Hi everybody, I am Mr. Folly, and welcome to me making the key for our formative 6.3 and 6.4. The image above represents N2 plus 3H2 yields 2NH3. What is the limiting reactant? So what I'm going to do is I'm going to start making this guy from these. So one of these takes 1, 2, 3. Second one, 1, 2, 3. Third one, 1, 2, 3. Fourth one, 1, 2, 3. So what do I have left over? Big blues, okay? So the limiting reactant is not big blues. It's the ones all gone. So what's the limiting reactant? H2. Those are all gone. What is the excess? The excess are the ones that are left over. That's big blue. That's N2. Okay. All right. I'm going to leave that there and let it pause. I know there was another picture here, but yeah, you get the idea. All right. So looking here. Get the equation A B4 plus CD yields BC plus AB2. So explain why these are both limiting reagents. Now, I don't even need this picture. Why are they both limiting reagents? They both, what does it mean if they're both limiting reactants? They both run out at the same time. Okay, so that seems a little weird here because I don't think that's true. That doesn't look like, yeah, well, that would be why they would both run at the same time, but it looks like this doesn't happen. Do you see how I have these guys left over? That's AB4. But AB4 is excess because it's over here. Okay. And, oh, I see why I was saying that. So there's none of these guys left. Woo, right? But there are some of those. So limiting reactant is CD because it's all gone, right? Because it made two different products. I guess I read that wrong. So they're both run out at the same time, but they don't. Let's see here. 4. Draw the products and excess reactants if necessary in the box on the right above. So I got to make this guy, and let's see if I can. Okay, so to make this guy, I need one of these and two of these. So I got a black. Why don't I call them B? So I got a black, and I got a red. So I got that in there. Now I got these guys left over. So I got 1, 2. I need one of those. So I got a red and a 1, 2 for the water. And I got the other red, and I got the other 1, 2. Okay. I'm going to do that again. So I'm going to make another one. I'm going to do, whoops, I want a black one. Do a black one here. It's going to be black. I'm going to get a red. I guess it takes two reds here, right? Black, red. Red. So we had black and I had red. And then I got these two guys left. So blue, red. Red, little blue. And then I got another one of those. Another red, the other half red. Little blue. So what do I have left? I got that guy left. That's it. All right. So what do I have left over? I've got one of those. So draw the products in excess reactant. So I got to draw this guy. So I got a black. And then I got a 1, 2, 3, 4. I got one of those. What is the limiting reactant? It's going to be the double red. So it's going to be red. Okay, I suppose I could actually use my color skills. That's my limiting reactant. Why? Because they're all gone, right? It's all gone. All right, particle diagram below represents the products of the reaction above. In the left box, accurately depict the reaction mixture. Pay attention to the number and type of atoms involved. So I'm just doing the same thing but backwards, and really it's the same thing. So I need to make CO. So CO, I'm going to go back to black. CO is going to be black, like that. Okay, so I've got to have CO, and then we have O2, which is going to be black and black. So those are the only ones I'm going to have in there, right? So let's see here. So I'm going to break this one apart, black, white, right? So that's going to be one of these, black, white, and then I got another black one left. So I got to do that again. So I got to have black, white on this one. So let's put one of the black ones this other way. Oh, this is so evil to do this way, right? So, I'm going to try this a little differently. So I'm going to use my coefficients here. Probably a better way to do this. So what I'm going to do is I've got two of these. So I'm going to take these two and I'm going to kill them, right? And when I kill them, that'll give me two COs. One C, one O. Notice how the two's from the periodic table, right? Two COs. And that's going to give me one O2. Okay, so I'm going to do it again. One, two of these will give me two COs, CO. And it's going to give me one O2. O2 is the double black rings. Then I have two of them left, two more. So it's going to give me two COs. So CO. And it doesn't matter which way you color it in, but it's got to be one white and one black, right? And I can even rotate them a little bit. Two COs and then one O2, which will be black and black. So there you go. And that's what it would look like. Okay. Oh my goodness gracious. Look at this one. The particle diagram above represents the reactants of the reaction above. In the right box, accurately depict the products. Pay attention to the number and type of atoms involved. Woof. So what I'm going to do is I'm going to get rid of two of these. Whoops. Control Z. Control Z. So I'm going to get rid of two of these and five of those at a time. 1, 2, 1, 2, 3, 4, 5. So when I do that, I'm going to make 4 CO2s. So I got my little key here. So CO2 is going to be C. So see how the coefficients help me? So I got to make 4 of those. So geez. There's 2. There's 3. There's 4. Okay, and then I got to make 2 H2Os. So H2O, O is got to make 2 of them. Then I got to make a stripy ear and another stripy ear. O that's colored in, and a stripy ear and another stripy ear. Okay, so we're going to do the same thing again. It's going to have 1, 2 of those guys, and 1, 2, 3, 4, 5. So right away I can tell, does it say, in the right box, accurately depict the product. So, okay, so I got to do it again. So I need 4 more CO2s. So 1 CO2, 2 CO2s, 3 CO2s, 4 CO2s, and color in those ears. And then I need 2 waters. So a black one with a stripy ear. I need 2 of those. I need another one, a black one with a stripy ear. And if you're wondering how I get these, I'm looking at this. Carbon, oxygen, hydrogen. Okay. And then what I have left over are these guys. So they don't have enough to make anything. So I got white circle, stripy ear, stripy ear. Got another one, white circle, stripy ear, stripy ear. Okay. What is the limiting reactant in the system above? Okay, so I have these are left over. So that means that O2 is the limiting reactant. Why? Because O2 is all gone. What do I mean by that? See how these are here and here? They're not all gone. So those are your excess. All right. One more. I hope this is the last one. Picture above is a representation of H2 and O2 in a sealed container. Which of the following pictures would be the best representation of the products if the reaction below were to run to completion? So let's run it to completion. So I've got to make water. Okay, so I'm going to have 2 H2, I got 2 H2, 2, and I'm going to have 1 O2. So when I do that, I'm going to have, and that's going to give me 2 H2Os. So there's 1, there's 2, and then I'm going to have left over double white ring. So this is what I'm looking for. So 2 waters and 2 double whites. 2 waters and, oops, I said 1 double white. There it is right here. All right, bust out your calculators and let's do this. What massive product forms? And I've got 6, and make this a little bigger for me. 6 grams of magnesium. And what massive product forms? So I'm looking for grams of MgO. So I hate 2 grams of magnesium. I'm going to go into moles of magnesium. 1 mole, 24.24. Is that the molar mass of magnesium? I'm going to ask Siri. What's the molar mass of magnesium? It's 24.12. 24.31. Bad memory. Bad. So now I'm in moles of magnesium, and I want to go into grams of MgO, but first I have to go into moles of MgO. Moles over moles use coefficients 2 and 2. And then I have 1 mole of MgO, and then I'm going to have 24.31 plus 16. 16 is oxygen, is 40.31. And that's going to be 6 divided by 24.31 times 2 divided by 2 times 40.31, 9.95. And then I like to change my color for my next one. So now I have 2 grams of oxygen, 1 mole of oxygen, 32 grams of oxygen, moles of oxygen, that's 1, moles of MgO, that's 2, 1 mole MgO, 40.31 grams of MgO, and then whatever number is going to be smaller is going to be my answer. So 2 divided by 32 times 2 times 40.31 is 5.03. I guess 5.04 grams of MgO is the amount that forms. What is the limiting reactant? O2, it forms least. How many grams of excess remain? Okay, so what I have to do for that, remember, is I'm going to take my limiting reactant, O2, so I have 2 grams of O2, and I'm going to convert it into grams of Mg. So 2 grams of O2 may look familiar, 32 grams of O2, 1 mole of O2, times coefficients, 1 mole of O2, 2 moles of Mg, times 1 mole of Mg, and 24.31 grams of Mg. And this will tell me how much I need. 2 divided by 32 times 2 times 24.31 equals 3.03 needed. And that's how much I need. Now remember, I have 6. So 6 minus 3.04 is 2.96 grams Mg excess. All right. In a different trial, the same reaction, 1.50 grams of O2 forms 3.02 grams of O2. What's the percent yield? So notice here I took away the limiting reactant part, but it's going to make 3.02 grams of MgO. So I'm going to take my 1.50 grams of O2 and convert it into grams of product. So I want grams of MgO. Times dividing bar, 1 mole O2, 2 moles of MgO, times dividing bar, 1 mole MgO, and then grams of MgO, which was what, 40.31. And this will be my theoretical yield. 1.5 divided by 32 times 2 times 40.31 is 3.78. That's expected. So what I get for my percent is part over total times 100%, which is going to be 3.02 over 3.78 times 100%, which is going to be 3.02 divided by second answer, 79.9, 79.9%. All right, resume, there we go. So now I have to do this reaction. I have 6.7 grams of Na, and I have 3.20 grams of Cl2. So what I have to do to find the limiting reactant is convert both of these into the same thing. So I'm going to convert both of them into grams of NaCl. So 6.7 grams of Na, make this bigger. Times dividing bar. I hate you grams of Na, and I'm going into moles of Na. I always go through moles, always go through moles, always go through moles, blah, 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 blah. Times dividing bar. Now, my goal is to get to grams of NaCl. So moles of Na on the bottom. I can't go right into grams of NaCl. I first have to go into moles. Moles over moles use coefficients. Moles of Na. Whoops, I put the wrong thing. NaCl. NaCl, and then grams of NaCl. Grams of NaCl is a good, little g means grams, and little g means go to the periodic table. So that is 58.45 grams over, of course, 1 mole. I'm going to put that math in my calculator in a minute. I'm going to set up this part now. 3.20 grams of chlorine times dividing bar. I hate you grams of chlorine. Remember, whatever unit you're giving up here, you hate that unit and put it on the bottom. Always go through moles, always go through moles, always go through moles. When I go to the periodic table, 1 chlorine is 35.45, so dose is 70.90. Now I'm in moles of Cl2, but again, I want grams of NaCl. Wrong unit. So I hate you, wrong unit. Moles of Cl2 on the bottom. I want to go into grams of NaCl, but first I have to go into moles of NaCl. Moles over moles use coefficients. 2, 1. Moles of NaCl, but I want grams. 1 mole of NaCl is 58.45 grams of NaCl. And that's going to have me get out my calculator. I'm doing the top one first. 6.7 divided by 22.99 times 2 divided by 2 times 58.45. And I get 17.0 grams of NaCl, maybe. Bottom one, 3.20 divided by 70.90 times 2 times 58.45 is 5.28 grams of NaCl. So what is the limiting reactant in the above reaction? So the limiting reactant is the reactant that made the smaller number. So the limiting reactant is chlorine. So it's nice and easy to find and circled. What mass of NaCl forms? This says 5.26, but I'm going to 5.28 for mine. 5.28 grams, that's the smaller number. Okay, so when you do your limiting reactant, usually nail 2 of them at once. Okay. All right, how many grams of excess remain? So remember to do that. I take my limiting reactant and convert it into my excess reactant. Limiting reactant, 3.20 grams of chlorine. Converting it into my excess reactant, which is going to be grams of Na. Okay. Hate 2 grams of chlorine. I always go through moles of chlorine. 1 mole is 70.90. I got that by go to the periodic table. I hate you moles of chlorine. I want grams of Na. Before I go into grams of Na, I go into moles of Na. Moles over moles use coefficients. I need to see my coefficients. 2 for Na, 1 for Cl2. 2 for Na, 1 for Cl2. I'm in moles of Na, but I want to be in grams of Na. And periodic table tells me this is 22.99. 3.20 divided by 70.90 times 2 times 22.99. is 2.07 grams of Na, and that's what I need. Okay. Now, remember, when I do my subtraction, it's based only on Na. So everything I'm talking about here is going to be Na. Grams of Na that I have, grams of Na that I need. So I'm going to do 6.7 minus 2.07, and that's going to be 4.63 grams of Na left over. Okay? All right. In a different trial, the same reaction, where Cl2 is the limiting reactant, 2.99 grams of Cl2 forms 4.71 grams of Na. So what I'm going to do is, again, convert chlorine into this, and this will give me a bigger number. This is my theoretical yield, which means it's the most you could possibly get. Does that kind of make sense? All right, so 2.99 grams of Cl2 times dividing bar. Hate your grams of Cl2. Always go through moles, always go through moles, always go through moles. Now, I'm in moles of Cl2, but I want grams of NaCl. Wrong unit. Hate you, wrong unit. Hate you, moles of Cl2. I want to go into grams of NaCl, but first I have to go into moles of NaCl. Moles over moles use coefficients, 2 and 1 from way up on the equation before. I don't know why I remember it, but I do. Now I'm in moles of NaCl, but I want grams of NaCl. 1 goes with moles, and little g means go to the periodic table. So when I add up 22.99 and 35.45, I get 58.44. And then I use my calculator. 2.99 divided by 70.90 times 2 times 58.44 is 4.93 grams of NaCl. Now that's my theoretical yield. That's not the percent yield. So remember, percent is part over total times 100%. So my part is what they told me I got right here. 4.71 over 4.93 times 100. 4.71 divided by 4.93 is 95.5%. Whoa. Whew. So now I have copper reacting with sulfur. So 80 grams of copper reacts with 25 grams of sulfur. So I'm going to make this a little bit bigger. So I'm going to start with my 80 grams of copper. I'm going to change my color because I feel fancy. So 80 grams of copper times dividing bar. I'm going to make my pen smaller too. Oh, maybe I'm not. I'm going to do grams of copper and a moles of copper. So I didn't talk about this much. 80 grams of copper reacted with 25 grams of sulfur. What mass of Cu2S forms? So I'm going to turn both of these into grams of Cu2S. Little g means go to the periodic table. Copper weighs 63.55. Now I'm in moles of copper, but I want grams of copper sulfide. So moles of copper on the bottom. I want to go into grams of copper 2 sulfide or copper 1 sulfide, but I got to go into moles first. Moles over moles use coefficients. So I've got a 1 and a 2. And then moles of Cu2S into grams of Cu2S. So copper is 53.55 times 2 plus sulfur is 32.07, 159.17, and that's 1. So I know before I waited to do my math, but I'm crazy different this time. So 80 divided by 63.55 divided by 2 times 159.17 is 100.2 grams of Cu2S. I'm going to change my color again, and I'm going to do 25 grams sulfur. 25 grams of S. Same idea. I hate you, grams of S. I'm going to go into moles of S. My goal is grams of CuSO4. Sulfur is 32.07 times moles of S. And I want to go into grams of Cu2S, but I first go into moles of Cu2S. I'm in moles of Cu2S, but I want grams of Cu2S. And luckily I did this one before. 159. Oh, I could write the wrong number. 159.17 in 1 mole. 25 divided by 32 times 1 divided by 1 times 159.17 is 124.4 grams of Cu2S. So the question is, what mass forms? The mass that forms is the smaller number. Okay. What is the limiting reactant? That is copper, because it made less, right? Your limiting reactant always makes less. What mass of the excess remains? Okay, so how do you find your excess again? So you find your excess by taking your limiting reactant and converting it into your excess reactant. My limiting reactant was kappa. My excess. My limiting reactant was kappa. So I'm going to start with 80 grams kappa. And I'm going to convert that into grams of S. That's my goal. So I hate you, grams of copper. I'm going into moles of copper. Copper again is 63.55. I got that from the periodic table. I'm in moles of copper, but I want grams of sulfur. But before I can go into grams of sulfur, I have to go into moles of sulfur. Moles over moles use coefficients, and from my balanced equation up above, mole S was 1 and kappa was 2. Now I want to get out of moles of S and go into grams of S. And 1 mole, go to the periodic table, 32.07. So let's see what we get. 80 divided by 63.55 divided by 2 times 32.07. Enter. And I get 20.1, which I hope is less than what they gave me. 20.2. Sorry. Erase. 20.2 grams of S. Oh, look, they gave me 25 grams of S. 25 minus 20.2 is 4.8 grams of S. All right, so now I think we got a percent problem left. Yep. The same reactions are formed where only 20 grams of sulfur react, but only 97.3 grams of Cu2S form. What is the percent yield of that one? So I'm going to convert my sulfur into my product. 20 grams of S times divided bar. Hate you, grams of S, going to moles of S. 1 mole is 32.07. And then moles of S and moles of Cu2S. Both are 1 over 1. That's from the coefficients. So if you look at the coefficients, you're golden there. Moles of Cu2S, grams of Cu2S. And I had that molar mass somewhere, but it might be quicker for me to just recalculate. 63.55 times 2 plus 32.07. 159, that even rings a bell. 159.17 in 1 mole. So 20 divided by 32.07 times 159.17 gives me 99.3 grams of Cu2S is my theoretical yield. That's the most I should be able to get. Now remember, percent is part that you got over the total possible times 100%. So that means the part that I got was 97.3 over the total possible 99.3 times 100%. Let's see what that is. 97.3 divided by second answer is 98.0%. And that's it. Woo! Awful lot of stoichiometry. Hope you enjoyed it. Toodles.